Okay, let me start with some opening comments. So we're in week 5, and you know by now this course for most of you is very challenging. There's a lot of work, the assignments are long, the labs are long, so you really have to start early. I know that's hard. But you really need to start early. You can't wait and try and do this in a day or even 2 days before the deadline. And people are asking me to extend deadlines, and in general, I am not going to do that. You got to start early. If your power goes out on the day that it's due, you should not be waiting till the last minute. Most of you are okay, but I haven't been able to check. I've been wanting to check. If any of you have fallen 6 grade items behind, you're at risk of withdrawal and you should contact me. Don't wait for me to contact you. Also, this week is a holiday on Monday, so the schedule is shifted 1 day out of the normal. But that will make next week shorter, so just try and finish everything by Sunday, even though the quiz is going to be on Tuesday. All right, this week we're doing the Millikan Oil Drop experiment. There is no new physics, but we're going to take pretty much everything we've learned this semester and much of what we learned last semester and combine it into understanding this landmark experiment done in the early 1900s by Millikan and 2 others. I forget their names now. So it's a good application of the physics we've learned in a landmark Nobel Prize winning experiment. Unfortunately, we're all virtual. We do have an apparatus similar to this apparatus, very similar, at HCC, where we actually do this experiment. And it's a challenging, technically challenging experiment, and unfortunately you will not have the opportunity of actually carrying it out. So with figures and diagrams, I'm going to try and explain to you what that experience would be like. Okay, how are you going to learn about this? Well, the video will be a good source. If you go to Moodle, you will see a folder on Millikan and the lab documents in there, and there's a spreadsheet in there, but there are 2 readings that you should read, one from Wikipedia and one from another source, about the history and the mathematics behind the Millikan Oil Drop experiment. So you have that. You have this video. And if you find other resources that you think your classmates might benefit from, post it on the Q&A forum. So watch the video and start the lab, the assignment and lab today. The lab isn't open yet because I need to make some adjustments due to the fact that you're not actually doing the experiment. You're not actually able to do the experiment. Okay, those are my introductory comments. I'm now going to start my explanation of the Millikan Oil Drop experiment. Notice the figures that I have. This is the apparatus that we would use in lab, or very similar to it. We have an older version. This is a person looking through the apparatus connected to voltmeters and other meters that are used in the measurements. This gives you an idea of the size and the scale. Usually we don't use this stand, we put it on a tabletop. But this is what it would be like if you were actually doing it in lab on this apparatus. This is Millikan's apparatus from over 100 years ago, like early 1900s, so 100 to 120 years ago. This is the apparatus he built and did the experiment to find the charge on the electron. This is a good schematic of the apparatus, and another one that we'll look at. And this is a diagrammatic detail of the chamber. So this is the chamber, but in reality it's just a tiny small cylinder, and so you're going to try and understand all that. So you use oil of a known density. It goes into the spray bottle. Here's the chamber. This is like a diagram magnification of this little tiny chamber. There's a lid that's not shown. You take the oil bottle, you squeeze it, you spray oil into the chamber, and you view the oil drops in the chamber through this eyepiece, and there's a light here that illuminates the chamber so that you can see the oil drops. And you get a size of the scale from this diagram up here. If we were in class, I would have this in class showing you, and then in lab you would actually use it. So we take this chamber and some of the other parts and we change the scale and we make this diagram. So here's the sprayer spraying oil into the upper part of the chamber. Then there's a plate, you can see the brass plate there with a tiny hole in it. And the oil drops, some of them find their way through the hole and fall through this chamber between two metal plates, which can be neutral or charged positive negative or negative positive. So we can set the field in either direction or no field at all. So with no field on, the oil drops, because of gravity, are going to go through, but because they're tiny, tiny, misty, microscopic oil drops, they will come into terminal velocity almost immediately, like dropping, I don't know, a balloon. It falls at a certain terminal velocity, right? Because air resistance and gravity become equal. We'll talk about that in detail. So you're watching, you're seeing droplets. Now they're not all falling at the same speed because the bigger ones will fall fast and the slow ones will fall slowly, just like raindrops in the air. And as you see them falling through, the first thing you do is you time the rate at which they fall. So you see them in the eyepiece, you'll see two marks, two lines. They don't show it here. I should get a diagram of that. And as the drop falls past the marks, you time it with a stopwatch, you and your partner. So you know how long it takes to go a measured distance, and that way you get its free fall terminal velocity. That'll be one important piece of data. Then, while you see that drop falling, before you lose it, you turn the plate voltage on. And if the drop is uncharged, it won't do any good. It'll just fall out of view. But if the drop is charged, if it has a charge, it'll either go up or down at a different rate. And if you're lucky, you'll get the charge on the plates right. The way this is now, this is positive and negative. So if the drop is negative, it will start to rise. And when it rises, the same thing happens. Air resistance acts against it, and so it will rise at a constant velocity. Faster or slower, depending on what? Depending on how strong the voltage is, depending on how big the charge is, and depending on the air resistance. So those are all things we're going to consider in detail later. So then what you'll do is you'll time how long it takes to rise and record that time. Then you'll switch the polarity of the plates, actually putting a force on it going down, and it will fall faster. And so in lab, what you do is you get the free fall time, the time forcing it up with the plates, and the time forcing it down with the plates. You get those 3 times, and from that data, the details I'll explain later, you get the charge on the drop. a simpler way of doing this that's very difficult technically, but mathematically it's simpler, is once you've seen the drop fall and you've gotten its terminal free fall velocity with no voltage, then you turn the plates on, and if it starts to rise, you adjust the voltage in the plates and you try and hold the drop suspended where the force of gravity down is going to be equal to the force on the charged particle of the electric field up. And if you're able to do that, which experimentally is very difficult, but if you're able to do that, then the solution of the charge on the electron becomes much simpler. And that mathematics is the mathematics that we'll try to understand this week in the assignment and the lab. Okay, I think I've covered all the important aspects of this. Let me pause and think. Okay, let's look at these two diagrams before I go into the physics and mathematical analysis. Here's just another way of seeing it, the apparatus, right? The chamber, actually, of the apparatus. The chamber is small, the eyepiece is big. Here, the chamber is big, and the eyepiece and the atomizer or sprayer are small. So you spray in, you get the drops, they go through. You have an adjustable voltage. You can turn it on or off. You can turn it with polarity one way or switch the polarity the other way, and by adjusting the voltage, you adjust the field, right? The voltage is like this, and the field is either up or down. Putting a drop on any charge of oil, any drop of oil that's charged. In fact, what you see, let me describe what you see, is you spray this in, you see the drops falling, you'll see a lot of them. If the very bright ones are big and they fall fast, the harder ones to see is you see them falling, you turn the plate on, and then what you'll see is some drops go up and some drops go down. So think about that. Why? Because they have different charges. How do the drops get well, some drops get a negative charge because they gain an electron, and some drops get a positive charge because they lose an electron. And the way they become charged, I didn't discuss this, is just the rubbing of the spraying, right? When we rub things, they charge. So you spray this oil in, and a lot of the drops, just because of the friction of the spraying, puts a charge on them. And so when you turn this on, if you could watch a bunch of drops at once, you turn the plates on, you'll see some go up, some will go down, and some won't change because some of them won't be charged. So that's kind of the visual experience that you have when you do the experiment. Now, this small chamber, in lab, we take it apart and we clean it and we put it together. So inside here is this detail. And I can see this is kind of hard to read, but I can read it. There's the lid that you spray through. The top, the lid's not on there. And then here's the cylinder that covers both parts of the chamber. So there are two parts inside. The bottom is a metal plate. Then there's a plastic spacer that sits on the plate, and then there's an other metal plate with a tiny hole in it that sits on top of that. And this plastic spacer is about a half a centimeter thick. That's something in lab that you measure with the calipers. And so that is the chamber here. Now on top of this, in the rest of the chamber, is the upper part where the oil is. And so by getting the plastic spacer, you know the distance between the charged plates, and knowing the distance between the charged plates and knowing the voltage that you choose, you can calculate the electric field. We'll talk about that later. And the electric field, which you control with the voltage, controls the force on the oil drops, right? The force on a charged object is Q times E. That goes back to week 2. So this is all the much of the technical detail of this experiment. So I'm going to stop. I did forget one thing. I probably forgot more than one thing, but I just thought of this. So a lot of what I'm talking about is in the reading, and so you should do the reading. So one of the things I didn't mention was this a radiation source. So Millikan, in his original experiment, had a radiation source. So the drops do become charged by spraying, but if you have a radiation source, you can also change the charge on them. So you can have one drop and see how it moves with whatever charge it has from the rubbing, and then you can open the window to the radiation source and you can change the charge on it and collect more data on that drop. The apparatus that we have at HCC, the radiation source is long since gone dead, and so we don't use the radiation source. But in the assignment, there are questions about the radiation source. Another question that shows up in the assignment that I didn't talk about is these drops are so tiny. They're so tiny that as they fall through the air, they jiggle around. They don't just fall smoothly. You'll see them jiggling around, and that jiggling around is actually an indication of the atomic nature of matter. It's called Brownian motion, and they're actually jiggling on atoms and clusters of atoms. And so that jiggling motion is a way that Einstein used to affirm the fact that matter is made of small particles. So that's how tiny the oil drops. They're not as tiny as atoms, but they're tiny enough to be affected by the atomic nature of the gas in the chamber, the air in the chamber. Okay. Now we discuss the physics. So keep in mind there are 4 different situations that you want to understand. The first is the free fall situation. So that means the 2 plates are shut off. There's no electric field. There's no voltage across the plates. There's no electric field between the plates. And the object falls at a terminal velocity because there are 2 forces which are equal and opposite. Remember that about Newton's second law. So the force of gravity is exactly balanced by the air resistive force. Sometimes this is called Fr for resistive force. I notice in the document it's sometimes called F drag, or sometimes I call it F air. This is the air resistance force. And you know about the force of gravity. It depends on the mass and g at the surface of the Earth. The air resistive force, you might say, oh, what's that going to depend on? Well, it depends on 3 things. It depends on the size of the drop, naturally, so there's the R. The other obvious thing it depends on is the velocity of the drop. So faster means more force, and it's a direct relationship between velocity and force and the radius of the drop and force. And this last thing is the Greek letter eta, E-T-A. It's like an N with a tail, and it's the viscosity of the air. I'm not going to write it out, but viscosity of the air. Okay, so that all makes sense. And those 2 are in balance when it's in free fall. The next one, these are all isolated, by the way, is if we are able to suspend the drop, then the force of gravity is down, and the force now holding it up is the electric force, which is Q times E. And you do need to know, we've seen this before, but you probably forgot, that E equals the voltage divided by the distance between the plates. This is for a constant electric field, and so it's the voltage which we measure and the distance which we measure. And we're not in lab, so you haven't used the voltmeter, but it's easy to measure the voltage of something with an inexpensive voltmeter. And you put one of the probes on one plate, one of the probes on the other plate, and the meter will read the voltage. And the distance between the plates, remember, that is the spacer between the two plates. And so this is how we get the electric field. And the charge is what we're trying to find, charge on the drop, and that's the electric force. And those have to be in equal and opposite, equal in magnitude and opposite in direction when the drop is held suspended. The two other situations that we do in the lab, when we do the lab, is, since it's generally impossible to find the right combination to do this, what we do is we find a falling drop, and we turn on the voltage, and as it goes up, we adjust the voltage till we get it to go up at a constant speed, because you won't be able to get it to stop. And so while a droplet is moving up at a constant speed, the sum of the forces once again are zero. But the up force is the electric field. The down force is always gravity, and the resistive force is always opposite the motion. So when the drop's falling down, the resistive force is up. But if the drop is going up, the resistive force will be down. And when it's moving, there's always a resistive force. That's why it's much better to do this, because then you don't have that third force. But the inability to do this forces us to do the measurements this way. And then it helps to get the additional data. So the drop is falling free fall. You turn on the electric field, it goes up like that. Then you switch the polarity, so it's no longer in free fall, but it's being forced down. And so there's force up, force down. That's when the field is on. And in that case, the field is driving it down, mg is driving it down, and the only resistive force is the force of air resistance. But even in that case, even if the drop falls fast, it will fall at a constant velocity, and so the sum of the forces is zero. So the mathematics behind getting the charge on the drop using these equations is very complicated. What we're going to do in the last section of the video is, using these two equations, come up with a way of finding what the charge on the drop is. Ultimately, that's what we want to do. That's what Millikan wanted to do. What I'm going to show you now is done in the document posted in the lab folder. So you can read it there, or you can watch this. And there are 3 steps. I'm going to go through them quickly because you can replay the video. So we start with the free body diagram on the right, and we get that FE equals FG, and FE is QE, but since we measure the voltage and the distance, I'm going to rewrite it as QV over D, because that's what E is, and that's equal to mg. And then when we solve for Q, we get a very simple result. The Q that we want is simply mg D over V. And the G we know. The D is the distance between the plates we measure. The V is the voltage. We measure that with the meter. But we don't know M. So we can't solve this till we get M. But M is what determines the size of the drop, and the size of the drop depends on, is related to how fast it falls. So we'll use this equation to get the M. So watch. So to get M, we turn to the free fall free body diagram, and since it falls at a constant terminal velocity, these two forces are equal, so we can write Fg equals Fr, or Mg equals 6 pi eta Rv, and we get M equals this. Unfortunately, we're not done because we don't know R. So now we have two equations but three unknowns, so we need a third equation. And the equation that relates the M to the R is the density equation. So recall that density equals mass over volume. And since it's an oil, we can know the density of the oil. And the volume of a drop, a sphere, is 4/3 pi r cubed. So if we use the density equation, we get R cubed equals this, or R equals the cube root of this. And so notice what we have. We have three equations and three unknowns, and the rest is just algebra. But it's actually difficult algebra because this is R cubed, and if I take the cube root and I substitute a cube root in here, it becomes a mess. So let me show you how we might do the algebra. But basically, you're done. You've got two free body diagrams with two equations and the density equation, and so between all these equations there were three unknowns, and so we can solve this for mass. We just have to do the messy algebra, and you can see that done for you in the document. You don't really need to watch this unless you like doing algebra, but the since the R is R cubed, and I don't want to substitute a cube root in there, what I did was I cube all of this. So I go M cubed and all of this cubed, leaving the R cubed, and then I just substitute this. So here's the R cubed, here's the rest of it all cubed, and here's the M cubed. But there's an M on this side of the equation, so when I divide by M, I end up with M squared. And so the M becomes all of this cubed square root, that's the 3/2 power, and all this left over because I have to take the square root of this side and the square root of this side because this is M squared. And there's my M. Now this M has to substitute in here. But you see there's a G there, and there's a G here, and there's some pi's here, and these numbers under the square root. So really what you need to do is collect all those terms and turn it into an expression that you can use to calculate Q for any situation. Now notice what we have. We have some numbers, a pi. We have eta, which is the viscosity of air, we know that. We have g, which we know that. And we have the velocity, but what we measure in the experiment is how far it goes in what time. So for the velocity, I substituted the y and the t. So these are all numbers that we know, including the voltage and the separation of the plates. And so we have all the numbers we need in this complicated expression to get Q. And the final processing of all this, you can refer to the document, and you can see even the final result is complicated. So what you're given is a spreadsheet that you can use to actually do the calculation for you. So I decided to add a little more to this video, and some of you I spoke to, I said I was going to redo the end of the video to choose an algebraic path that followed the algebra in the posted document. But I think I'll just leave this here. This is only a couple minutes of algebra. But what I'm going to do now is I'm going to spend a few more minutes running you through the algebra in the document in case you have a hard time following that, and making a few points along the way. Okay, here's a second approach that's more aligned with the approach I took in the document. So there's the two diagrams. Here's the equation for this free body diagram. Here's the equation for this, and here's the third equation, the density equation. And so we have three equations and three unknowns. Just to remind you, the unknowns are the Q we're looking for, the mass of the drop, and the radius of the drop. Those are the only things that we don't know. And so with three equations and three unknowns, we can get what we want. So in this case, I'm going to start with this equation. And I solved the density equation for mass, right? Mass is equal to volume times density. So mass equals volume times density. So substitute this expression in here and solve for R. Go ahead, do that algebra. Substitute this in here and solve for R. So notice what I did. I took the M and put it here and set it equal to this and got this. And when I do that, I see that there's a pi on both sides, so that nicely cancels out. And there's an r cubed here and an r here, so I cancel that. I change this to an r squared. Then I multiply both sides by 3, divide both sides by 4 rho. And also what you'll notice I took the v and I changed it to y over t, distance over time. And so I'm left with this expression for r squared. And so in the assignment, the first thing you're asked to do is to get the velocity. And then once you have the velocity, you're asked to get the radius. So it's easier to solve for the radius than the mass. And then once you have the radius, you can use this equation to get the mass. And once you have the mass, then you can go back to this equation and get the Q. Or what happens in the assignment is you're actually given the Q and asked to find the voltage. So for that question in the assignment, use this equation, solve it for voltage, multiply both sides by V, divide by Q, and then put all those numbers, including the mass that you previously found, and you'll be able to get the voltage. So this is a much simpler solution. I'm not going to, the rest of it you can see. If I wanted to eliminate mass, then I would have to go through the same thing that I did the last time. And you can see all that. That's still quite complicated. You can see that on the document. And again, remember, you have a spreadsheet that will do some of these calculations for you. One more thing that I'm going to tack on here. So when you, in the lab, when we did it in the lab, the apparatus doesn't look like this, but here's the eyepiece and it shows you what you would see. So what you would see is this round eyepiece view, and you'd see all these little drops, which are actually very hard to see. And then there would be these two lines. And so you would time them between lines to get the velocity, going up or down or in free fall. So that's the view you would have from the eyepiece, and this is sort of what it would look like. In the assignment problem, there are actually 10 grid lines because we also have another apparatus that has 10 grid lines in it. In fact, if you were doing this experiment with modern technology, you would not look through the eyepiece any more than a scientist looks through an electron microscope or a telescope. They interface that with a video detection device that puts it on a computer screen. So you would actually watch the oil drops on a computer screen, and here you can see there are many grid lines. And if this were a video, you'd see the drops falling unless the plate was turned on. And actually on the computer, you could program the computer by pressing a button to measure the distance and the time and calculate the velocity of the fall for you. So this would be, here's the apparatus. And what it has is a video cam looking through the eyepiece, and that images are put on a computer screen where you can observe it there.